Believe it or not, something like this, or even this, can be turned into valuable tools, and I'm going to show you how in this video.
Hi, I'm Dennis Frechette and welcome back. In this video, I'm going to be talking about a pretty basic approach to heat treating scrap steels and turning them into useful tools. Now, this is another one of my reference videos, and the links to all the other reference videos in this series that are currently available are going to be in the description. So as I add videos to this series, you'll see that list in the description grow. So if you find one of these videos, go in the description and you'll see a list for all the other videos that are currently available. First off, I just want to make this very clear that this is a pretty basic and oversimplified approach to heat treating steel, and it basically is based on plain carbon steels. We have no way as blacksmiths of evaluating any other elements other than carbon content in a steel. So anything that comes into a blacksmith shop basically turns into a plain carbon steel, whether it's a $100 a foot space age steel or whether it's a crowbar. If it goes in the forge and heat treats like plain carbon steel, it's plain carbon steel. It doesn't matter how it started off its life. Once it's gone into the scrap pile, it all turns into plain carbon steel because that's basically all we can deal with. We have pretty simple heating equipment for the most part, just a forge, maybe torches, that kind of a thing. And we have a spark test to see if there's any carbon in here or how much carbon in it. So I know it frustrates a lot of people, but that's where terms like low carbon and high carbon came from. It's not determining any one type of steel. It's just the basic test that we've used to see if there's enough carbon in this steel to make it work for us. This is the process that I use. I've been using it for almost 50 years now. The people that have taught me this were using it for longer than that, and then it goes back for thousands of years. The first blacksmiths that discovered that, carbon in a steel made a difference, they came up with this process, and it's still around today, and it's still going to be a magical and mysterious process 200 years from now. So this is how you go about it. Hope it helps you out. Most of the steel that I use and recycle into tools are either coil springs, leaf springs, or crowbars. I like them because they're readily available, they're fairly cheap. The coil springs and the leaf springs are usually free, and the crowbars, go on sale at our local hardware store fairly readily, and they're really at a good price. So they're easy to get, basically. And the other thing that I like about them is they're very recognizable. Doesn't matter how far gone these things are. If you look at these three steels, anyone over the age of 10 is going to be able to tell you where these steels came from. So there's no way to confuse these three pieces of steel with anything else that you have in your scrap bucket. So this is one volume from a set of encyclopedias that I grew up with. It's the Popular Mechanics Do-It-Yourself Encyclopedia, and there was a series of 12 volumes, and it covered just about everything under the sun. This is the 1955 edition of the Do-It-Yourself Manual, but I'm sure a lot of the articles went back a lot earlier than that because there's a lot of crazy stuff going on in these pages. If there was something in common use in the 1950s, this book showed you how you can build it with pipe fittings, old Model T parts, and discarded farm equipment. And it may come as no surprise to you, but this is where I learned how to heat treat steel. It's a very simple discussion on heat treating steel. It takes metallurgy and strips it down right to its bare minimum. And it just gives you a workable process that you can use to recycle scrap steels into tools. And it's the process that I use today. Everything that I've shown you in my videos is basically this article recycled over and over again. The first thing you're going to notice when you start forging out a coil spring, or in this case a section of crowbar, is that the extra carbon content in the steel makes it a lot more difficult to forge. So it's going to take a fair amount more effort to forge, and the changes are going to happen more gradually. You can't force it into shape the way you can a piece of mild steel. Also, you're going to have to work at a higher heat and keep a very narrow forging range because Carbon steels do not like to be forged at a dull red heat. Forging at a lower heat causes a lot of stress in the steel, and those stresses, if they're not resolved, can result in warping or cracking of the finished piece in the quenching process. So you have to realize a steel with a fairly high carbon content is still brittle even though you can heat it up and forge it. So there are a few considerations when you're working with a higher carbon steel, but basically up to this point, the forging process is pretty much identical to anything else that you would forge. The heat treating process allows you to change the physical characteristics of that simple forging and turns it into a tool. For mild steel, the heat treating process is barely noticeable, but it does have an effect. And with higher carbon steels, you can make the steel so hard it'll actually shatter if it's given a good knock. And the whole heat treating process relies on a very specific temperature. And to underscore its importance, it's actually called the critical temperature. At this precise temperature, it's possible to make some pretty amazing changes to the working qualities of the steel simply by controlling the rate at which it cools back down to room temperature. And for that reason, it's really important to get this right. Now, the problem with the critical temperature is that the first indicator that people usually use is the color range on the bar, and the backup check to all that is whether the steel is magnetic or not. Now, the problem with the color range is that's totally dependent on the light levels in your shop. If you have a fairly well lit shop, then by the time you see the color ranges that they're suggesting, you're well above the critical temperature. And the problem with using a magnet to check for the critical temperature is that it is true that the steel is not magnetic at the critical temperature, but it's also true that the steel is not magnetic from that point on. So from the critical temperature until the steel is molten, it is not magnetic. So if you wait too long to check for magnetism, that's useless as an indicator. So here I have a demo to show you what I'm talking about. In this case, I have a lot of the lights turned off in my shop, so it's fairly dark. The normal light levels are like 10 times what you see here. And when I pull the bar out, it's that nice cherry red that everyone's talking about. Oh, that's great. It's at critical temperature, and it is not magnetic. But in reality, I'm actually well above critical temperature here. So at this point, I've turned off pretty much all the lights in the shop, and I've let the bar cool down quite a bit. And you can see, even in a dark shop, this is a barely visible dull red. And there's a little bit of magnetism. It's losing its magnetism, but there's still some stickiness there. So this is just below the critical temperature, and it's barely visible in a dark shop. If I had the lights on that I had before, this would not even show up as a color at all. So here I've given it just a little bit more heat. It's brighter, but it's not dramatic. And at this point, it is no longer magnetic. So this is the critical temperature for this steel. So if I heat it beyond this point, it'll still be non-magnetic, but what I'm going to be doing is the grain structure within the steel is going to keep getting larger and larger the more I heat it up. Here you can see that I've heated the bar up quite a bit more, and there's a very noticeable difference in the color range, and it's still non-magnetic. So this is probably very similar to the first sample that I did at the higher light level, and it barely showed up as being red. And here we can see that it's really well above the critical temperature. But I'm going to keep going just to make a point. So here again, it's hotter still, but we're checking it with a magnet, so most people would think, okay, we're still in the critical temperature range, but as you know, we're well above it now. And the grain structure is still getting larger. And the larger the grain structure, the weaker the steel is. So even though the outside of the steel may appeal hard and this file will skate off it, and all the usual things. The internal structure is very weak because it's very granular, and the steel is literally starting to blow apart. So here I've skipped along. The bar is basically at a welding heat right now. I'm giving it lots of oxygen to start burning off the carbon, and you'll see the fireworks here in a second. This is basically the steel starting to disintegrate. So here I'm taking it right out and putting it right in a bucket of water so I can freeze that grain structure so I can let you have a look at it. So here's the piece right out of the quench. That jagged edge was a huge crack, and I basically broke it off just by snapping it with my fingers. So here's a look at the inside. You can see how coarse the grain structure is. So even if I had gotten this tool to work, if it hadn't cracked and I was able to temper it and put an edge on it, the first time I used this tool, it was shattered just because the internal structure just isn't there to support a cutting edge. But here is the magic of the heat treating process, and especially the critical temperature. This is the same chisel. I did not grind away any of the edge. I threw it back in the fire, brought it up to the critical temperature, although this time I wasn't looking at the color. I just kept checking magnetic as the temperature rose. And as soon as it wasn't magnetic, I took note of whatever the visible color was, made sure that it didn't go above that temperature. I held it at the critical temperature for a couple of minutes, and I let it cool slowly so that the grain structure could reform. And then I brought it back up to the critical temperature and quenched it in water so I could break off the edge and show you the difference in the grain. So this is the proper grain structure here. The shiny edge on the top is where I used an angle grinder to create a fracture point so I could break off the end of the chisel and show you a clean line of the grain structure. And here are the two grain samples together, and you can really get a clear picture of how different the grain structures are. What you're looking at here is actually a clip that I've pulled from an earlier video that I made, and what you're going to be looking at is going to have really nothing to do with what I'm going to be talking about for the next couple of minutes. But at the end of all this, there is a clip of the quenching process, and it's probably one of the best clips that I've ever filmed. So this is giving me some room to ramble on until I get to that point. When you're done with your project and you're ready to turn it into a working tool, the first thing that you need to do is relieve any of the stresses that may have been put into the tool from the forging process. And to do that, you bring the working end of the tool up to the critical temperature. You'll hold it there for a minute or two, and then you'll let it slowly cool back down to room temperature. For a simple tool, it's good enough to just cycle through this process one time, but if you have a larger cutting edge that's fairly delicate, it's worth the extra effort to cycle through this process a few times to make sure that you relieve as much stress as possible. The next step in the process is to harden the edge, and once again you bring it up to a critical temperature. However, this time you quench it and cool it very, very quickly. The most common type of steel that you're going to run into, especially if you're sticking to coil springs, leaf springs, and crowbars, is going to be an oil quench. It's the mildest quench out there, so industry likes it because it just causes fewer problems. If you're sampling another piece of steel and the oil quench didn't harden it, then your other option is to quench it in water. That's the other most common quenching medium out there. If that doesn't produce a satisfactory quench, then you either have a sample that doesn't have enough carbon to produce a hard enough quench, or it's some strange alloy that needs to have some specific heat cycle to get it to harden. So in either case, it's not something that you can use in a regular blacksmith shop. So set that aside and go on to the old standards like a crowbar, leaf spring, or a coil spring. And the standard test for hardness is to use a file and see if you can get it to bite into the surface. If it simply skates across the surface of the steel, you do have a fully hardened edge and you will be able to make a usable tool out of this. If it bites into the surface, either you've missed something in the hardening process or you have a steel that doesn't have enough carbon to make a useful tool. The last step of the process is to polish the cutting edge and reheat the cutting edge to a very low and very specific temperature. This process will soften the edge slightly and reduce some of the brittleness that was caused from the hardening process. So the two processes together give you a working edge. And unlike the hardening process, this is all about the colors that are produced on the surface of the steel, and these colors are very predictable and very accurate. These are called oxidation colors, and they are the colors that appear on the surface of a brightly polished piece of steel. They're very accurate and they're very reliable, and they're the reason that the tempering process is usually described by a color rather than a temperature. So at the low end of the scale, you have sample number 1, and this is a polished piece of steel with no heat applied to it. So this is what you're starting with. Number 2 is the first visible color that you see, and it's usually referred to as a light straw. Number 3 is a few degrees hotter, and it's usually described as a dark straw. In number 4, the straw color kind of transitions into more of a bronze color. Number 5 is kind of hard to describe, but it's sort of a darker bronze. Sometimes it has reddy patches to it. In 6 and 7, that patchy color disappears and it starts to transition into a full purple. 8 and 9 is usually described as a peacock blue. In 10 and 11, the colors are starting to get lighter again, this time in a blue range. And by the time you get to the end of the scale, there is basically hardly any hardness left in the steel. So there really is no practical applications for these because they're just a little bit harder than the soft steel that you started with. Now that's what the color temperatures look like if they're fired in a kiln that has a really accurate temperature control system. In the field, they're going to look a lot different. First of all, they're all going to be bunched into a pretty narrow band, and the mid-ranges are going to be really hard to distinguish. So what I'm doing here is I'm using a torch to heat up a section of the tool that's fairly far away from the cutting edge. I'm going to keep heating this section until I see the first visible colors show up on the polished end of the blank. Now this was a tool that was quenched in oil, and you can start seeing the oil starting to burn off right now, and that happens just before you start seeing the straw color. So at this point I'm going to ease up on the torch, and I'm just going to apply the heat when I see that the colors are starting to slow down a little bit. So here you can see an example of what I was talking about earlier. All the color samples that I showed you are just bunched into that one narrow little strip. And this happens because the tip of the tool is still relatively cold, and where I'm applying the torch is very hot. So that compresses all the bands into one narrow strip. So what I'm going to try to do now is give it as little heat as possible so that the temperature can start to even out and those color bands will start to get wider. I'm working on a cold chisel here, and the color I'm looking for is sort of that darker straw just before it turns into that bronze color. So what I'm going to do now is really go easy on the torch because I want that color band that I'm looking for to be as wide as I can get it by the time it reaches the tip. When I get the color range that I'm looking for at the tip, it's okay to quench the tip of the tool in water to stop the heat from progressing any further. This tempering color is going to give me a pretty tough cutting edge, and the wide band that I have right at the tip is going to allow me to grind this tool quite a bit before I get into the softer color ranges, and then at that point I'm going to have to repeat this whole process and retemper the tool. And of course the final test is to see how it cuts.